All right, good morning and welcome to the APNIC e-learning session. Today's session is going to be on IPv6. And just to remember that this will be an overview session. So we will be discussing more of basics and concepts and just for you to introduce you to IPv6. Now, to introduce myself, my name is Chappika and I work as a training manager at APNIC. End of this session, we will be having a little survey as well, so feel free to fill that. Once you have completed that, you will be directed to the training materials so that you can download the materials as well. All right, now in this session, what we are going to cover, basically what is IPv6, and then we will give you a very brief introduction about the protocol and background and so on, and then what sort of functional improvements are there comparing to IPv4. We would assume that you are familiar with IPv4 so that we can have a comparison there. And then we have a module on addressing, basically to discuss about the different types of addressing we have in IPv6 and then how these addresses are being taken care of. And then also we have some information about protocol header comparisons, and then going into bit details on the host configuration side. So mainly discussing about this concept on interface IDs. And then also we will have some section on the prefix delegations and how these addresses are being distributed and they can be managed as well. So this is the kind of overview that we would like to discuss in this introductory session, which we will be covering in the next 1 hour or so. Okay, let's get started. Now, what is IPv6? So now we know that we have been working with IPv4 for quite a long time. IPv4 was there since like mid-70s or so, and since then, you know, there has been lots of usage or utilization of IPv4 addresses. So before we really talk about IPv6, just to let you know that in IPv4 we have some limitations that especially in terms of the address space, because in IPv4 it's a 32-bit address or 32-bit address space that what we have, which means there is a limitation of the number of addresses we can have, which is 2 to the power of 32. So during, you know, early 90s or so, when these IPv4 addresses, I mean until up to about early 90s or so, when these IPv4 addresses has been distributed to various networks around the world, and then there was a situation that there was a risk of actually running out of these IPv4 address space at the time. So the researchers, the scientists and so on, so they realized that this matter, and then they have started working on some new protocol. So IP version 5, which was there, in fact, I mean, it was one of the experimental protocols that they worked on at the time, called Internet Streaming Protocol. But then, of course, IPv6 was the sort of standard, because IPv5 has been already used. So some people, in case if you wonder why we are moving from v4 to v6 and what happened to this v5. So IPv4 was actually previously it was also called as IPNG, or the IP Next Generation Protocol, and then later it was identified as IP version 6. So this was a little bit on the history aspect. Now here, as we know, we are discussing, or we are focusing on the TCP/IP structure, as we know in data communications. So you have your different layers of TCP/IP, you have your application, the transport and internet and physical and so on. So our focus here, when we discuss about IPv6, our focus here is going to be on the IP or the internet layer here. So previously we had IPv4 when we discuss about the IP layer or the internet layer, and now we introduce IPv6. So it's a matter of focusing on the IP layer. Now, this is a very sort of quick background on what has been happening. I briefly mentioned you earlier that since around 1990s there has been work going on. The first wake-up call about IPv4 exhaustion was actually happened around in early 90s. You can see that in August 1990, but since then, of course, IETF, the Internet Engineering Task Force, they have been working on the new protocol, and they have been working on based on this. There are several working groups, so and then they have been focusing on this IPNG, and then later on the IPv6. So the in December 1998, the updated version of IPv6, or in fact the RFC, which is RFC 2460, which came up, and then the organizations that distribute this IP address space has been following this RFC to distribute this IPv6 address space and to utilize this IP address space. And now the important point here is that, okay, now we try to, so just something about we want to actually mention that IPv6 is not something very new, right? It's not something which started like last month or last year or even a few years ago. So as you can see, it has been there for more than a decade, or in fact more than that. Since early 90s or so, there has been some work going on. So it's not something new. But why there is some big interest now? Because, as you know, the IPv4 address space has been depleting all this time, and basically, you know, we have been distributing IPv4 address space all this time, and for many, many years. So we have come to a stage where we have very limited amount of IPv4 addresses, and also the internet has grown to such extent where even nowadays the applications, the communication we do and so on, you know, we need to actually optimize in terms of protocol level. That is also why, comparing to IPv4, there has been some more focus in IPv6, actually focusing on the current needs of communication, basically. Because back in 1970s or even 80s and so on, when we focus on IPv4, it was quite different type of communication we used to do. I'm talking from data communication point of view. But now it is different. We talk about, you know, video streaming, audio streaming, and so on, mobile IP, and so on. So there are many things that we will need to optimize in comparison to the protocol design. So address depletion. Now, talking about the address depletion, in IPv4 we can have 32 bits, so 2 to the power of 32 bits, which is like 2 to the power of 32, that is around 4.2 billion IP addresses. That's what we are talking about. But if you consider about from today's term, even we have a world population of more than 7 billion, I would say. So you have more than 7 billion, and if every person in the world needs to get an IP address, we still don't have enough IPv4 addresses there. And also the future internet is actually going to be more on things rather than, you know, computers or any other, you know, machines that we used to deal with in IPv4 world, right? In fact, nowadays, even at this point of time, also we use in many places in the world, we use lots of IP-based devices, things like home appliances, things like, you know, various other devices and so on, where we can actually use IP addresses, right? Even if you think about mobile phones and so on, you know, we use many of these devices during our day-to-day basis. So talking about IPv4 numbers, it's not really enough. So that is why actually it is important that we need to focus more on the IPv6 aspect. Now, IPv4 side, again, you know, just to let you know that the current situation is that from internet registry point of view, Internet registry from APNIC point of view, from Asia Pacific point of view, we are into the last /8 of IPv4, which means when we distribute IPv4 address space, there are some limitations, or in terms of the address space size, there are some limitations that the organizations can receive the amount of IP addresses from the registry. So currently, if any organization requests for an IPv4 block, they can receive up to /22, which is 1024 IP addresses. So 1024 IP addresses is really might not be enough, especially for a big network, or especially for a network with lots of devices, or more operation around different locations and so on. So you know better about your network. So if you think that you need more than /22, then you will have to look into other alternative ways to get the IPv4 address space. When I say alternative ways, either it could be from as a transfer or any other technologies and so on. But then again, all these things are pretty much very temporary type solutions, right? They're not very permanent type solutions. But talking about the future, right, in terms of scalability and so on, so it is always important to focus on the IPv6, because that is kind of the way to move forward. So that's why the importance here, why we need to think about IPv6 and why we need to talk about IPv6. So here you can see that in the slide there are some figures given here. IPv4 has got 4.2 billion addresses. As we said, it's not very much enough for our requirements nowadays, whereas IPv6 address space, theoretically you can have a very big address space, 3.4 into 10 to the power of 38. Even, you know, it's very hard to define this number as well. It's quite big address space. Now, again, you know, later on when I talk about the address distribution, I will let you know that the distribution mechanism is not really like IPv4, because in IPv4 we used to actually, you know, we used to give these or distribute these IP address space on certain way where even every address mattered. But in the case of IPv6, it's very hard to actually calculate each and every of these addresses. So there are certain ways that we distribute these addresses as well. Okay, now there are of course new functionalities and new improvements comparing to IPv4, which we will be talking pretty much in this slide. All right, so new functional improvements. So you can see that in the first place, the IPv4 address space has increased from 32 bits to 128 bits. So you saw the big numbers that v6 can have. And then also we have this feature called stateless auto configuration. So stateless auto configuration is something similar to plug and play, or actually, you know, when you connect IPv6 device basically to a network, it should be able to generate the IP address automatically. In v4 world, yeah, we had things like DHCP, where a DHCP server would give an IP address, but that is not stateless. I mean, also, you know, you can even configure things like manually, the IP address manually as well, and in IPv4. So you can still do those in IPv6 as well. You know, either you can configure the IP address manually or through a DHCP server. But in addition, we also have this feature called stateless auto configuration, where based on the properties of your physical address, you can actually generate the IPv6 address automatically. So in this way, you don't have to manually configure, or you don't even need to have a DHCP server to actually give the IPv6 address. So this is quite useful, especially when you think about consumer appliances and so on. Let's say, you know, if you get some, maybe a fridge or a washing machine, something like that, you know, when you try to, you know, if it is IPv6 enabled, you know, if you connect that to your home network, it should be able to automatically configure the IPv6 address. You don't, you know, you cannot expect anyone to actually go and manually configure the IP address for that, right? So that's why these sort of features are quite important. And also in terms of header sizes, in IPv4, comparing to IPv4, we have a fixed header in IPv6 with a 40 byte, and the size of the header is 40 bytes. A good thing about that is it's a fixed header, because in IPv4 it was not a fixed header. It is variable, so all that means actually, the devices, the routers, when they process these, there are lots of overheads to process those v4 headers. But in comparison, in IPv6, the devices, the routers, they don't have to spend a lot of CPU power to process those v6 headers. Hop-by-hop segmentations, path MTU discovery. This is again, in terms of MTU. In v6, we have this path MTU discovery where, let's say, from source to the destination, if there are lots of routers, for example, in the middle, they don't have to do all the fragmentations, right? Because depending on the MTU size, the source can do the fragmentation and then send these packets, basically. So the routers in between, they don't have to actually do fragmentation. So this is again, so in this way, basically, the routers in the middle can actually again process the packets faster, or do the processing quite fast, and then forward the packet quite fast. And then there are built-in features for multicast and anycast groups. In IPv4, IPv6, we use multicast and anycast. And multicast is basically, you can send the packets from one interface to a group of interfaces, whereas anycast is kind of you send to a group ID, but to the closest of that group. So we could use these type of addressings as well. And then also there is, from mobile IP point of view, in v4 we had this issue of triangular routing, whereas in IPv6 it is quite simplified as well. Now, from security point of view, we also have IPsec, things like IPsec. Basically the security in the IP layer. In IPv4, it was there, even IPsec was there, but you still have to enable that. Whereas in IPv6, IPsec is enabled by default, so you don't have to, separately have the IPsec on top of that. So, and then also in IPv6, we don't have normal broadcasts, unlike in IPv4. So these are again, some of those features that they have introduced in comparison to IPv4. So in terms of addressing, I mentioned you that there are different types of addressing that we have in IPv6. We have Unicast, Anycast, and Multicast. So Unicast is basically sending a packet from one interface to another interface, whereas Anycast is sending a packet from one interface to a group of the nearest of a group of interfaces. And then multicast is you send from an interface to a multiple interfaces. So we have facilities or different addressing models to address these different types of requirements. In terms of protocol comparison, you can see that you have IPv4 header versus the IPv6 header. You can always see that IPv4 header had got quite a lot of fields there, which means you need to, the device, the router has to do quite a lot of processing in terms of identifying different fields and then processing those requirements. So in comparison, in IPv6, actually some of those fields have been removed, and it has also been distributed to different other layers as well, because in the TCP/IP layer we have the transport layer and so on. So some of these things can be handled either in the transport layer or even in application layer and so on. And so the red areas which are shown in the IPv4 header, those red areas has been removed in IPv6. You don't see those. And then The dark blue one also, it's newly introduced, the flow label. This is mostly to actually handle the quality of service, QoS, and things like that. So if you really see, in IPv4 also we have this header options field, whereas in IPv6 we don't have those. We can actually have a header extension instead, and in this way we can keep the header quite simple in IPv6, and the whole purpose of this is to reduce the workload for the for example, for the router, right? So that the routers can process these packets quite quickly, and handle or read these headers or process the headers quite quickly, and forward the packets, right? And in terms of the size, so there are 10 basic header fields in IPv4, and that has been now reduced to 6 header fields in IPv6. In terms of the header size, actually, this header size has increased, of course. You can see that because in v4 you have 20 octets or 20 byte header, whereas plus it can vary up to 60 or so, depending on the options. Whereas in IPv4 it is not like in IPv6 it is not like that. In IPv6 we have fixed headers, 40 bytes, 40 octets, so the processing can be much faster. Now, in terms of addressing, we discussed that we have 128 bits in IPv6, 128 bits. So in 128 bits, we have 8 fields, right? In v4, we have 4 fields, 32 bits. So each field is 4. So each field is 8 bits, or in other words, 1 byte in IPv4. Whereas in IPv6, it is 16-bit fields, because there are 8 fields. So 128 divided by 8, each field we get 16 bits. So if we are to then define this 16-bit, just like in IPv4, it's not going to be very easy, because in IPv4 we define these by decimals. That's why we see these like numbers like 203 or 159.10.1, for example, right? Whereas in IPv6 it's going to be very difficult, and also it's not going to be very simply can be simplified if we try to define these in decimals, because we have 16 bits in every field. So 16 bits can go up to 2 to the power 16, which is like 65,536. So, and then we have 8 fields. So 65,536 means 5 digits. So 5 digits into 8 times, you can even end up with like 40-digit number to define an IPv6 address if we are to do it in decimal, which is actually, it's not the way that we do. So instead we define, or we represent it using hexadecimals, because it's the base of 16, and we can actually represent the 16-bit field quite easily with hexadecimal values or digits. Now we have 16 bits. The thing is that what you need to understand here is that the hexadecimal representation. So for example, think about let's say decimal 8. Right? So decimal 8 in binary we define 1000, and then even in hex the representation is 8 in hexadecimal. But when it comes to, let's say, decimal 10, the binary representation is 1010, and then the hex representation is A, right? Because after 9 you have A, and then B, C, D, E, F, up to F. So F, the binary representation is 1111, and the decimal is 15. So if you see that pattern, you can see that every hexadecimal value can be defined or represented by 4 bits, right? By 4 bits. So if you have 4 bits to represent one hex, now every field we have 16 bits. So we can then represent every field of an IPv6 address by using 4 hexadecimal values. So this is why actually you can see this example starts from FE80. So FE80 is in hex values, and F is in binary 1111, and E in binary is 1110, and 8 in binary is 1000, and 0 in binary is 0000. So if you add all those things, you get 16 bits. So every field in IPv6 can be represented using hexadecimal, and the total number of bits in every field is 16. So this is something that we will need to understand if we are to define, or if we are to represent IPv6 addresses. So 128 bits, so this is a very typical example of an IPv6 address. So you have 8 fields, 1, 2, 3, 4, 5, 6, 7, and 8. And every field is separated by a colon. So if you see here, you can see there's a colon. In IPv4, we used to have a dot, but in IPv6, we now have colons to differentiate those fields. Now, still, this is going to be pretty long, especially this example that we have shown here can be quite long. But generally, when you get a prefix, since there are lots of 0 bits can be involved, there are some simplification rules we can introduce to simplify these IPv6 address representations. Now, if you see this example, which is given here, 2001 0db8, this IPv6 address. So this can be further simplified to a very convenient level. So if you see this, one of the rules where we have in IPv6 simplification is that if you have 0 zeros, the leading zeros basically, you don't need to actually write those because that doesn't contain or carry any value there. For 2001, we still have to write these zeros because they have a value there. So 2001, we write that. And then, but in the 0db8, we don't need to write 0 there. We can just write db8. And similarly, if you have 0000, you don't need to write all the zeros. We can only write 10. That's enough. And similarly, this 0000 is another simplified into a 10. And similarly, this field again simplifies into a 10 here. And remember, these are all hexadecimal values. They are not binaries, okay? And then we have 03E6 here, so that gets simplified into 36E. And then we have 1250, but this 0 of course contains a value, and then we just have to write that whole figure there, 1250, and then similarly 2B00, which comes here, 2B00. And there is one more simplification you can make here. You can see there are further zeros, 0 fields are repeating here, 0:0:0. Now, if you have some 0 repetitions, there is another rule where you don't need to write those repetitive zeros. So which means you can omit these zeros. So then we have this colon, and then we have the ending colon there. So which will then create kind of a colon type representation, which is again identified as a null value. This is what we call a null value. So if you have zeros repeating, you can actually have a null value there. And then we can write our rest of the address, 36E1250 and 2B00. Only thing what you need to actually be aware is that you can only have one null value, right? Only one colon, only one colon in a single address. Because if you tend to put 2 colons, then there is ambiguity. Means we don't know how many fields can be inside every of those colon representations. This is why we only use only one colon value there. Okay. All right, so that was about the how we actually can represent IPv6 addresses. Now, next thing is, okay, how can we distribute all the addressing structure? How do we actually define the addressing structure here? So we have 128 bits of address space here, you can see that. And then we divide this into two parts. We have our network prefix. This is actually the network prefix or the global prefix. And then we have this interface for something called interface ID. Now, interface ID is defined as 64 bits. So if you get your 128-bit address space, out of that, the last 64 bits, the trailing 64 bits, they are identified as the interface ID. And then let's go to our network prefix now. Right, in the network prefix, you can see in this is a very specific case where we have actually mentioned about an ISP, but this can be the case for any organization who would want to come and receive a prefix from the internet registry. Let's say in your case, if you want to come and receive a prefix from internet registry, you can then you can actually get a /32. So this /32 is the prefix that the internet registries would delegate to an organization that comes and asks for an IPv6 block. So, but obviously, if they have a larger requirement, if they can justify for it, they can get more than that. But the minimum allocation or the minimum delegation that what we make is a /32. So what do you mean by really /32 here? /32 means your network prefix has got 32 bits in it, right? So from here to here, the first 32 bits are given to define your network, basically, right? Network prefix. And then, unlike in IPv4, we need to be a little bit careful how we are going to delegate this address space to further to your customers or to your downstreams and so on, to your end sites and so on. Because in IPv4, we can decide the subnet based on the requirement. Let's say in IPv4, if you are given a /22 from the registry, and if your customer, let's say, needs 10 IP addresses, for example, into their network, so if they need 10 IP addresses, you can give them a /28, right? Because theoretically, /28, that subnet can have 2 to the power of 4 IP addresses, which is like 16, of course, but practically you can use 2 less than that. So, but still, for 10 IP addresses, that's /28, that is enough. Okay, so that's how you decide that. And similarly, if any of, let's say, some other customer comes to you and asks for, let's say, 200 IPv4 addresses, you can give a /24, right? Something like that. And so you decide based on the subnet requirement. But in the case of IPv6, there are recommended guidelines how this address space can be distributed. The main reason behind this is actually to manage our routing tables in a proper way. Because if we actually decide any prefix that we like, or if we just actually don't stick to some certain proper best current practices, these routing tables can grow very, very fast, especially in IPv6. The main reason is it's very hierarchical because we have 128 bits of address space, so the tree hierarchy of IPv6 is quite deep. So the moment that you deaggregate or break these blocks and break into small blocks and delegate those, then our routing tables can actually increase rapidly. So this is why we try to actually stick to some best current practices and then do these delegations in a proper way. So in terms of IPv6, I mentioned you that the registry gets a slash. Registry gives their members a /32, just like what is shown in this slide, and then from the member level, if they want to further delegate to their, let's say, downstream ISP, they can go up to a /48, right? Because I'm talking about delegations or allocations where you make to your downstream ISPs. In turn, they would make further delegations to others, right? So you have 16 bits of address space here to do that, right? 16 bits of address space. So for example, the ISP, if I'm taking an example of an ISP could get a /32 from the registry, and they can further delegate maybe a /40 to one of their downstreams, or /36, and so on, right? Now, when it goes to the end-site level, right, if you're talking about end-site, means operational networks, they are not going to further delegate to others. They will stay in the end-site. So these are given for operational networks. So those address blocks can be at the size of from between /64 to a 48, right? Between 64/64 to a 48. Now the definition here is that each subnet in IPv6, the recommendation is to have as a /64. Each subnet, one subnet is a /64. So as an ISP, you can decide exactly, your inside, your customer side, depending on their requirement, how many subnets they would need. If they only need one subnet, you can give them a /64. If they need, let's say, if they are a kind of enterprise type network or a small medium type organization, inside you can give something in between, maybe a /56, because /56 comes in between a 48 and a 64, right? And then if the inside is a large inside, then you may even give a /48, right? /48 inside. So this is actually the guideline. So these boundaries are quite recommended boundaries, where if you want to further delegate or further assign to your customer sites or end sites. So /64 for a single subnet, and then /56 actually for let's say a medium type enterprise, and then the /48 for a large sort of end site. Okay. Now if you actually do a little bit of calculation here, how many end sites, actually, let's say how many large end sites that you ISP can have or organization can have out of their /32, that's quite a lot, because if you divide /32 by /48, you get a figure of 2 to the power of 16. So 2 to the power of 16 comes to something like 65,536. Right, 65,536. That's a lot. So you can have that many large end sites, large customers inside that /32 that you receive from the internet registry. Now, let's say if you go to one of those /48s, now you remember, as an ISP, you may be able to have like 65,536 of those have a big end site. If you go to one of those, you can have 65,536 subnets inside that end site, because subnet size is /64. So if you divide /48 by /64, you can have 65,536 subnets inside that, right? So you can actually imagine how big is this /32 itself, right? You can give to 65,000 odd end sites, and each end site can have 65,000 odd subnets in it. Now, if you actually really see how many IP addresses can fit in every subnet, that would be 2 to the power of 64, because we have 64 bits. Subnet size is /64. So 2 to the power of 64. So 2 to the power of 64 is really a big figure, right? In IPv4, the theoretical limit of total IPv4 address space is 2 to the power of 32, right? Because we only have 32 bits. That's which comes to 4.2 billion, right? So if you think about 2 to the power of 33, that gets double. So 4 billion becomes 8 billion. 2 to the power of 34 becomes 16 billion. And here we are not talking 2 to the power of 30s, or not even 40s, not even 50s. We are talking 2 to the power of 64, right? 60s. So you can see actually every single subnet can have quite a lot of IPv6 addresses, and they are quite big. But sometimes you might wonder, okay, why do you need to give this much of IP addresses in a single subnet? I mean, think about the reason I told you earlier. If otherwise, obviously, if you make very small subnets, or if the registries delegate small blocks to the organizations, and when they announce these prefixes to the global routing table, it can increase quite fast, and then there can be so many routing table entries in the routing table. If you consider from IPv4 point of view, we have around 500,000 routes now in the IPv4 routing table, and sometimes even it's hard. Some organizations find it's hard to handle even 500,000 prefixes, and that's why they do even filtering and so on, right? So here we are not talking like in millions. We could be talking in billions or even more, right? So this is the risk. So maybe in the future, if the router memory technologies improve and so on, the things can be different. But at this point of time, this is one of the concerns actually, why we actually need to make sure that the routing table is kept on a place where we can actually manage it easily, right? So that's the sort of distribution or the addressing structure we have in IPv6, and then go into device level. We have every device is a /128, just like in IPv4 every device or every address is a /32. In the same way in IPv6 every device is /128, because we have 128 bits in IPv6 address. Okay, now if you remember the previous slide, the last 64 bits I mentioned about the interface ID, right? So this lower order 64-bit field, it is there to generate basically the client side. In other words, the device, the host side of IPv6 address. I mean, the reason behind this is, let's say, I mentioned even earlier that in IPv6 we are looking into the future, and we are expecting so many household devices, home appliances, and these kind of things, which needs to be actually generate their own IPv6 address. So which means, in the future there could be more and more of these devices around us. So this is also why actually we will need to have a fair bit of space for the lower order, not for the prefix but for the lower order, so that we can actually satisfy those demanding address requirements, right? So we have 64 bits. Now the last 64 bits, generation of these last 64 bits can be done in various ways. One option is, of course, you can do it just like what we do in IPv4, which is to configure the IPv6 address manually. So you get your prefix from your upstream provider or the registry, and then you can work out your last 64 bits based on your addressing scheme, and then you can actually work out the address manually. That's one option, just like what we do in IPv4. We configure the IPv4 addresses manually, right? And then the other option is you do this through DHCP, right? Through a DHCP server that can actually give the IP address and that can generate that. And then the other option actually is to this is a new feature in IPv6. Earlier I mentioned you auto configuration. So that is to use or generate the last 64 bits automatically. How it happens? Automatically this IP address is generated based on the physical address of the device. So when I say physical address, basically the MAC address. So we know that device has a MAC address of 48 bits. So that 48 bits is taken into consideration in terms of defining that 64-bit address. So this mechanism is called EUI64. It's a standard, right? EUI64. So in the EUI64 mechanism, the 48-bit MAC address is used and we generate the 64-bit interface ID. Now, we don't have to do this manually, right? It is done automatically. And so we don't need to really worry about how it happens and how the address what it generates and so on. So it happens automatically based on your MAC address, right? So there is a sequence because MAC address is only 48 bits, so it needs to insert extra 16 bits. So 16 bits is actually 4 hexadecimal values because each hexadecimal value is 4 bits. So 16 bits needs 4 hexa values. So that there's a sequence that how EUI64 algorithm, it will insert that 16 bits into your MAC address and generate the 64 bits. Okay. So that's what we call EUI64. And then the other mechanism could be just to generate these 64 bits using kind of a random algorithm, or what we call the auto-generated pseudo-random number. Because some of the vendors, manufacturers, they might worry that possibly using the MAC address can be a reason to actually to work out the MAC address of the device and so on. So that is also why actually it is possible if you do a random sort of generation, that concern is not going to happen. Okay, so maybe in the future there might be some possible methods coming up in the future, but these are the methods actually what we do at the moment in terms of generating the interface ID. Okay, now going to the other side, the global prefix, global network prefix, you can see that earlier we discussed about different types of addressing models. We talked about Unicast, Multicast, and Anycast. So in the case of Unicast, I told you that those are the IP addresses. In other words, the packets are being transferred from one interface to another interface, and those are the address models or address prefixes that we use for our usual networks. So when you come to the internet registry, or even when you go to an ISP, and when you request for this address space, IPv6 address space, what you get is what we call this IPv6 global unicast prefix or address. Now we have a range for this global unicast prefix. Now in this range there is a prefix, or the first 3 bits of this prefix is being reserved as 001, right? So if you see 001 as the first 3 bits of your address prefix, that means we can work out exactly what would be the range for it. Because if you have 001 as your first 3 bits, the 4th bit, the next one, the first address would be a 0, right? This X can be 0. So when the X becomes 0, right, we have 4 bits. So the 4-bit field gives us then 0010. So 0010 in hexadecimal, that is 2. Right, that's 2. But still we are talking about only 4 bits. And every field in IPv6 has got 16 bits. So we still need to then account for another 12 more bits. In other words, 0 bits. So that's why we have 2. This represents 0010. And then the rest of the 12 bits are all zeros, so which means 000. So if you consider this 2000 and then rest of the bits are all zeros anyway, so that's why we have colon there. So if you see this prefix 2000 ::/3, because the prefix length is 3 bits, this is the prefix that we use as the global unicast prefix. So it's a /3, and the range of this global unicast prefix is 2000 ::3. And the last address of this range is when this x becomes 1, because that's the last bit. So when the x becomes 1, it's 0011. 0011 is actually 3, and then the rest of all the other side of the address is all ones. So which means when you add all ones, convert that into hexadecimal, we'll end up in all these F values. So that's why this is considered as the last address of that. So you know exactly first address and the last address, so you can work out the range. So basically, when you request for IPv6 addresses, you will be getting these addresses from that range. So you can see that currently all the regional internet registries in the world, they are given a prefix of /12 from IANA. Right, IANA is the body that keeps the central pool of these addresses. So if you consider the APNIC region, we have this prefix 2400 : you can even say : /12. 2400 : /12. So that's the /12 that we have received. Out of this /12, we distribute /32s or whatever, the blocks that our members are requesting depending on their requirements. Okay, and different, just like that, you can see all the other internet registries also, they have their different other prefixes that they're delegating from, but the important thing is they're all coming under this range of global unicast. Okay, now you can actually get a feel of how big is this IPv6 address space. This is just to show you, all available address space is the whole area. Out of this global unicast range is only this yellow area, because /3 is actually 1 out of 1/8, because /3 means 2 to the power of 3, that is 8. So if you divide this into 8, one of those 8s is the size of this /3, right? And if you zoom into that, that's your global unicast space. And then out of that, if you see all the 5 RIRs, they are given /5/12s, and that 5/12 accounts only to this little blue line you can see here. It's a very minute blue line. You can see that inside this yellow line, and that's the whole space given for the whole world, or all the RIRs at the moment. And then all the RIRs, they distribute, a /32 out of this /12 to member. So you can have so many /32s inside a /12. In other words, 2 to the power of 20, right? 2 to the power of 20 /32s inside that /12. So that's quite a lot, right? So you can now get the feeling about how big is that IPv6 address space, and also exactly if you need an IPv6 address space, what is the size that you're going to get. And next thing is how to get the IPv6 address space. Now if you're an APNIC member, it's very easy. You come to APNIC and just request for IPv6 block. We have, in fact, if you have IPv4 address space, it's a matter of just one click to ask for IPv6 address space. You're already a member, so you can get a minimum allocation, which is a /32 in IPv6, right? Depending on, of course, your requirement. But if you are not an APNIC member, you will need to, of course, one option is to go to your upstream provider, upstream ISP, and get IPv6 block, or you can directly come to the Internet Registry and become an APNIC member, and then get an IPv6 allocation from APNIC. Okay? And if you visit APNIC website, you can find more information about this process. And if you have any questions, you can always talk to our help desk. Now, finally, you can also see some stats on IPv6 routing table. You can see that almost we have around 14,000 prefixes announced in the global routing table. So good thing is you can see that IPv6 routing table is increasing in a sort of a rapid direction, rapid way, or a kind of an exponential curve as well here. So comparing to IPv4, of course, there's a big difference, because IPv4 BGP table, we have around 500,000 prefixes, whereas IPv4 still, is around 13,000, 14,000 prefixes at the moment. So there's a big difference there, but good thing is that there are more and more day-by-day organizations, networks, they're announcing IPv6 prefixes. So this is something that you can think about as well. And if you don't have IPv6 address space, you can get this address space either from the Internet Registry or from your ISP, and then you can start working and testing, experimenting with the IPv6 blocks that you receive. Okay, and this actually ends this basic or the overview session on IPv6. And if you have any questions, I'm happy to actually take any questions now, or if not, we also have other e-learning sessions on IPv6. We go further into things like doing subnetting, further address planning, and migrating from IPv4 to IPv6, things like that. We also have other e-learning sessions as well. Feel free to attend those. And today we have few more e-learning sessions coming up. We're going to discuss more about reverse DNS side, and then this is not about, of course, the next session is not going to be about IPv6 focus, but in general the reverse DNS side, and then we have some few more sessions on internet resource management area. So if you have any questions, I'm happy to take any questions now. If not, it would be great if you can fill this feedback form for us. And then you will be directed to the training materials as well. Or I have actually just sent the link to the chat window, so you can click that in case, so that will take you to the survey form. Okay, and if you don't have any questions, and thank you very much for your participation, and feel free to send any training queries or questions to training@apnic.net. Right, training@apnic.net. And finally, we also have some information page, website on IPv6 at APNIC. This is quite a resourceful page where you can find quite a lot of information about IPv6, all the way from getting IPv6 address to training, and then what's happening around, and all these various information with related to IPv6, right? And then finally, if you have any further questions, feel free to talk to our help desk. We have a chat line, and also you can find more information through our website as well. If you want to write to our help desk, that's helpdesk@apnic.net. Okay, and if everything is okay, and thank you very much for your participation, and we look forward to seeing you in future e-learning sessions.